Hi, I'm Michael.
I am Hima Sameera.
Hi, this is Saideepak.
We're Group 5 and we're presenting the research paper on Virtual Filtering Platform, or VFP, a virtual switch platform for host SDN in the public cloud. The author of this paper is Daniel Firestone, an employee of Microsoft. Next slide. All right, so let's get to the main topic. What's the current problem happening right now? Well, the explosive growth of public cloud environments. We're seeing an unprecedented need for server infrastructure and on a scale for millions. So this isn't just quantity, it's about having the right amount of quality as well. Modern public cloud platforms must support increasingly rich network semantics. These include private virtual networks, load balancers, access control lists, and many other features that customers would expect. All these capabilities must be delivered consistently with scalability and with minimal latency. So there's more VMs now, there's more rules, and there's more complex components. So the major question is, how do we solve this? How do we build a scalable and high performance switch that can support all these complex network policies while also allowing independent network controllers to program the switch without interfering with each other? So the key issue is scaling this efficiently and securely. Next slide. Okay, so there are existing solutions out there. The industry has exports many options. This includes Open vSwitch or OVS. This provides programmable forwarding. There's OpenFlow, a protocol for configuring network devices. VL2, a virtual layer 2 architecture. And Anata, which is a layer 4 load balancer. So Microsoft Azure has a collection of all these individual filter drivers for each network feature. And this can grow to get really complex because of all these number of features in there. Next slide. So, what are the shortcomings of all these existing solutions? Well, they either don't scale well, they lack that flexibility, or they can't handle these advanced stateful rules. Most are either stateless and support only single controller models, and this creates bottlenecks in the multi-tenant cloud environments. They also offer very limited support for dynamic rule updates and hardware offloading. OVS lacks multi-controller support and has no built-in mechanics for stateful policies. For example, if you need to implement connection tracking for security groups in OVS, you need external components like contract and also adding all sorts of complexity for potential performance bottlenecks. It's OpenFlow, another example, it also introduced tight coupling between components. It forces static rule chains that can't really adapt to the change in network conditions. So when a new flow arrives, the open flow switch must either consult the controller before handling the packet, and this introduced latency, which is that's not good for the at a cloud scale. There's also hardware offloading in OVS. It's very challenging because all the complex rule table chaining. I guess for example, implementing VXLAN encapsulation within all the different security groups in the hardware, it would require a lot of coordination between all the different rule tables. Makes it really difficult for at the cloud scale, makes it really difficult to optimize. Most problematically, most of these solutions require reboots for updates, which interrupts service and impacts customer workloads. Like, imagine having to take down thousands of VMs just to update network policies. The operational impact will be enormous, will be intense. These limitations made it clear that a new approach was needed for cloud scale networking. Next slide. Next slide, please. Okay, so what's the opportunity for innovation here? Well, this is where the Microsoft's virtual filtering platform comes in, or VFP as we're called for this presentation. It's a fundamentally new approach for virtual switching. It introduces modular programmable switching directly on the host. What sets VFP apart is its support for stateful layered high-performance SDN policies. It scales to millions of flows and integrates seamlessly to Azure infrastructure. So by implementing these complex network policies right on the host, VFP reduces dependency on core routers, and this improves security delivery and network performance. And the reason it's designed this way It allows the physical network to remain simple and fast while pushing policy complexity to the edge. So it's modular, it's host-based and programmable, meaning there's more control per VM with less overhead. And this all aligns perfectly with this distributed nature of cloud computing, where intelligence at the edge often provides more scalability than centralized control. All right, next slide. Again, this is more the opportunity for innovation. This is more of a graph scale of it. Next slide. All right, so what is the major motivation of VFP? So we need to recognize that public cloud providers face a lot of pressure to implement all these network features at a massive scale. So this includes virtual networks, load balancing, ACLs, the quality of the service, and all these are deployed across millions of servers. Traditional core routers and hardware solutions, they really can't implement all these policies and all these features at such a good scale. The cost will be enormous, will be huge, and the resulting system would really be inflexible. Host-based software-defined networking, it emerges as a scalable solution that allows physical networks to remain simple and fast. It pushes complexity to the software layer on hosts, where cloud providers can achieve better economics while maintaining high performance. So that's the major motivation behind VFP. It creates a more scalable, flexible, and economical network infrastructure for the public cloud with connection-based policies. So the major problem VFP would address is how to build a scalable and high-performance programmable switch in the cloud. Public cloud networks will require support from millions of flows from all the different features wants to include, while allowing multiple independent controls to program rules without conflict. So, as I stated, the key issue is how to scale this efficiently and securely. Next slide. All right, now let's break this down. What is the major design and main idea for VFP? So we're going to start with the whole architecture structure of VFP. At its core, VFP functions as a forwarding extension on the Hyper-V extensible switch. This design allows VFP to leverage existing Hyper-V infrastructure while adding sophisticated SDN capabilities. So VFP sits between the virtual switch and network adapters, both physical and virtual. When a packet arrives, whether it's on my VM or the physical network, it passes through VFP before reaching its destination. And this positioning, it allows VFP to apply policies right at the point in the packet's journey. So VFP connects virtual NICs to policy enforced VFP ports, and it creates a flexible framework for network policy enforcement. Each virtual machine has one or more virtual NICs, each connected to a dedicated VFP port, and it serves as a chapter point for all the policies within network traffic. And these ports act as gateways where all the VM traffic must pass. So this design supports deployment in both native and virtual environments, and it makes it very flexible to all different infrastructure requirements. Where VFP, it can be deployed on physical servers for either the bare material networks or in containerized environments or within nested virtualization scenarios. So the big thing about VHP, what makes it so powerful, is how it applies SDN policies directly right on the VM host traffic. So this eliminates all unnecessary hops between traffic, between different hosts. It reduces latency. So instead of sending traffic to a specialized network appliance for processing, VFP can apply these complex policies right at the source or destination hosts. So this architecture follows like a whole layered approach, and this enables multiple controllers to coexist with each other without each other's policies. VFP also includes good caching mechanisms to optimize performance. So VFP also supports stateless and stateful processing. So stateful rules treats each packet independently, while stateful rules track connection state in a policy and apply policies based on the context of the connection. So the stateful capability enables, quite good security policies and network address translation that wouldn't be possible with stateless processing alone. So now transition to the next slide, which will be talking about the match action table or the map model. This is the core component of VFP design. So it has two parts. Each rule has two parts. The first is the match condition that determines which packets the rule applies to. And the second is the action that should be taken when a match occurs. So match conditions can be based on any field in a in the packet header. This includes IP addresses, both the source and the destination, MAC addresses, different port numbers, the protocol types, and even custom metadata. VFP supports complex matching with wildcards and ranges all set based for precise control. The actions can include allowing or dropping packets, network address translation, encapsulation in protocols, or even changing quality of service markers in different customizable actions. So VFP's implementation of the map model supports all user-defined actions. You can customize it however you want. So this you can be very flexible with this. User-defined actions allow policy controllers to implement custom packet processing beyond standard action types. Rules can be added, can be modified, however you want. And the stateful nature of VFP rules is very important since for these network policies for a track connection state, while traditional ACLs are stateless and treat each packet independently, VFP state capabilities automatically track established connections and allow return traffic. So this simplifies this whole process. That's in the next slide. Is we also have multi-control support. Each controller manages isolated features within VFP, preventing interference and ensuring policy isolation. This is critical since all these environments with different policies need to coexist in conflict. So, in a common environment, for example, one controller may apply virtual network functionality, one may apply security, one may apply quality of service policies. So, each control operates independently. Honestly, think about this like the OSI model, all these different layers within the network, like application, uh, internet, MAC addresses, etc. So all this separation, it simplifies the network policies. So the multi-controller design emulates all these bottlenecks. So it achieves better scalability and resilience. So if one controller fails, it only affects that specific layer, while the rest of the system continues to function. This improves overall reliability, and this promotes scalability, safe and scalable SDN development, and allows different teams to work together quite well. And again, this isolation nation is very safe. It's good scalability. So now I'm gonna hand it off to Hima to talk about the next topics.
So now let's discuss about layering model, which is one of its most critical architecture which we use in VFDs. As you can see, it's a policy implemented across multiple layers per port. Each layer handles one function, examples like ACL, SNAD, and etc. And it's also bidirectional support for inbound and outbound policy, which also ensures consistent treatment for symmetric traffic flows. So, which is basically like VFP organizes network policy into modular layers so that each layer performs one job, such as ACL filtering, NAT, or tunneling. So, what's special about this model is that this structure allows independent SDN controllers so that you could manage a separate layer without conflict. Like for an example, let's take a firewall controller can manage ACLs, as we know, while another manages NAT. So each get isolated from other. So this separation makes the system more scalable and easier to debug. And the novel contribution of this layering model in this particular paper is that it is enforced multi-layer SDN control plane that is both modular as well as bidirectional, which is something prior systems like OpenFlow lacked. So next, move on to this stateful policy support. This is another area where VFP stands out from previous virtual switches, like it tracks flow states like TCP and UDP handshakes. Rules create paired inbound and outbound flows. It enables features like firewall, stateful NAT, and load balancers. and also crucial for enforcing fine-grained connection-based policies. So as we all know, traditional switches are stateless. They look at each packet independently, but real-world policies like firewalls and NAT requires connection awareness. So this is where VFP addresses this by tracking full TCP and UDP flow states, including handshakes, timeouts, and signals, so that this VFP creates a paired flow, one for outbound and one for inbound. And these are linked to the VFPs so that it can understand and enforce symmetric rules across the connection. And as I read the paper, the authors demonstrate its effectiveness with production deployment, showing hundreds and thousands of concurrent flows per port working reliably. And this confirms the solution works and it enforces symmetric rules across the connection. Now let's move on to unified flow table, where this slide is about the performance in VFPs, and it is also VFP's main optimization tool. So here, as we can see, caches flow action after initial packet, and it enables fast matching for future packets. It optimizes performance at large scale, and it reduces per packet latency and CPU overhead. So basically, it's like when a packet arrives first, then VFP processes it through all the layers. But once matched, VFP saves the result in UFT so that the future packets from the same flow can skip some layers and use the cached result directly. So it's like I have seen this flow before, so I know exactly what to do. It's based on that example. And also, it's like this dramatically boosts performance, especially in the VMs, which are running at high bandwidth, like 10 or 25 GB and etc. And and this real metrics from Azure Data Center to show that this works in practice. And not only that, this also proves that the system is not just theoretical, it is optimized, tested, and production ready. And next, let's move on to header transposition model, where this model helps in like push, pop, modify, and which is used for NAT, tunnel encapsulation, decapsulation, and also works on metadata for efficient processing, and also flexible and programmable packet transformation engine. So we already have the model UFT and etc. So along with the UFT, VFP also uses called a header transposition model for rewriting its packets. As a header transposition is the role-based way of modifying headers like source, destination IPs, port numbers, MAC addresses, and etc. So this is like a key operations for NAT, tunneling, and encryption. So how this works is inside the hard coding tunnel behavior or separate modules, anything. VFP lets controller define exactly how headers should be modified in a programmable way so that it could reduce the complexity while increasing the flexibility. I mean, this is like a clear example of smart and cloud scale engineering. And let's move to the continuation of this, that is transposition engine. I mean, we looked the hood at how VFP combines performance, programmability using its transposition engine. And now this transposition takes the matched rules from each layer and builds a composite action like NAT, tunnel encapsulation in one step. So it's like mix the NAT and plus tunnel encapsulation so that the composite action is cached in the UFT for the future use. So it's mostly, as you see, it doesn't touch the raw packets. It only operates on past metadata. and it's a key to the VFP's low tenancy processing, and it combines action across layers to complete header transpositions. Next, let's move on to the fast path versus slow path, where the fast path, as you can see, it's a first packet of a flow is processed through all rules, whereas fast path, remaining packets use cached compiled action. It also enhances performance and resources efficiency, enables real-time packet handling at a line rate. So this fast path is critical for Azure, while performance matter and every microsecond counts. So the author shows that real results, orders of magnitude faster packet handling with the UFT and fastpath. So yes, they absolutely achieve the performance goals as we can see in the paper. And next, let's see this fire flow reconciliation. So this uses generation counters to detect changes in policy, ensure the system is always up to date, and each flow is stacked with policy version creation for easy tracking. And let's say if the policy change or expires, then the old flows are invalidated upon access, but it still maintain the policy consistency. And also this particular method ensures consistency with very little impact on system performance. So basically, if I tell in one line, so this is like uh, uh, no, VFP use generation counters and stuff. So this allows live policy updates without dropping flows or restarting or rebooting the services. So this is helpful in that part. And when the flow is created, it's tagged with the current version, like the current policy. So if the version gets outdated or expires or any rule changes in the particular policy, the flow is revalidated automatically the next time it's used. So what happens by it is that without rebooting and restarting, it incredibly uses new features for any cloud platform, especially one operating at Microsoft Azure. And it not only delivers a programmability and performance, but is also designed for operational reliability. So next, move on to this offloading to hardware, where offload tunneling protocols like VXLAN and NVGRE to the NICs for efficient processing. SRIV enables exact match rule offload to the NIC, reducing CPU load, and NIC enforces policies at line rate, ensuring no CPU overhead and high-speed performance. And also, offloading avoids the need for costly TCAM lookups, optimizing overall network efficiency. So basically, this hardware offloading works as this makes VFPs cloud ready and future proof. So VFP offloads work like VXLA and tunneling and checksum processing to the NIC, reducing the CPU load. And not only that, and more impressive way with SRIOV, it offloads entire flows so that NIC can process packets without involving the operating system at all. So by this, what we can achieve means VMs in Azure hit 25 plus GB, as we all know, with less than 25 microsecond or below. So all while consuming almost no host CPU. And I mean, that is like a massive achievement for us. And these also aren't the lab simulations. The authors present real world deployment numbers, millions of flows, and heavy number of traffics, and also proven the scalability after using the offloading to the hardware. I mean, so what we learned from this, we learned that modular, stateful, programmable SDN at a host is not just possible, it's already deployed at a massive scale. And so now I'll be handing over to Sai for the further. Thank you.
Thank you, Hima. From now, I'll take over this presentation. Coming to the scalability focus, the system is deployed across over a million Azure hosts, providing its ability to scale at a massive level, serving cloud environments globally. It supports 10 to 20 layers and thousands of rule groups, ensuring flexibility and extensive policy management across the network. Each port can handle up to 500K concurrent flows, which guarantees high throughput and optimal performance even under heavy load. So next, coming to the isolation and safety. Each layer is isolated, ensuring that no control or configuration from one layer impacts another, which increases security and stability. Controllers are responsible for only the designated layers, which simplifies network management and reduces potential errors. By isolating the layers, the system reduces the risk of misconfigurations that could affect the whole network, ensuring reliability. The isolated layers make troubleshooting easier by confining issues to one layer, reducing downtime and improving maintenance efficiency. Next, coming to the programming model summary, VFP uses a modular architecture where everything is an object, whether it's a port, a layer, a group, or a rule. This abstraction helps simply management and enables scalable policy definitions. Each object has a clear role, which keeps configurations clean and modular. The platform provides a set of powerful APIs for lifecycle management, like creating, updating, and deleting these objects on the fly. This allows for dynamic and programming control of the networking pipeline, making it easy to automate deployments. Rules are highly configurable. Each rule can define match conditions like IP or port, set a priority to determine evaluation order, and specify actions such as allow, drop, or mirror. This gives us very fine-grained control over traffic behavior. All of this is tied together with the VFP API, which is optimized for performance. It allows us to rapidly apply changes to the data plane without sacrificing throughput, making it ideal for large-scale and real-time environments. And next, coming to diagnostic and monitoring tools. VFP offers extremely rich telemetry, tracking over 300 real-time metrics for each port and flow. This includes throughput, error rates, packet counts, and more. It gives operators and tools deep visibility into what's happening inside the network at any given moment. In addition to general metrics, it keeps a close watch on performance, critical indicators like latency, explicit congestion notification marks, retransmissions, and how many flows are currently active. This helps in identifying congestion and performance bottlenecks early. You can take a full snapshot of a pod state, including rules, counters, and flow history, without impacting the live traffic. These snapshots are useful for offline diagnostics, auditing, and forensics, especially in scenarios where real-time analysis isn't feasible. Now, coming to the next part, which is implementation. Uh, VFP is built on Hyper-V, and it is designed to run directly in the kernel space as a lightweight filter. By being tightly integrated with the Hyper-V switch, it can process packets at very high speeds with minimal overhead, ensuring optimal performance in virtualized environments. One of the key benefits of VFP is that it works seamlessly with the native Windows networking stack. There's no need to modify or replace existing applications or infrastructure, so it integrates smoothly into your current network architecture. It's specifically engineered to provide low latency packet processing with minimal impact on the CPU. This allows the system to process high volumes of traffic while maintaining peak performance even in the demanding environments. And coming to the next slide, VFP policy object model. The ports are fundamental units in VFP while policy filtering is applied. Each port is typically associated with the virtual NIC, and it's the point where traffic enters or exits a virtual machine. So the layers are implemented as match action tables. These hold the policies that define how packets should be handled for inbound traffic. Layers are processed in reverse order compared to outbound traffic. ensuring correct rule application based on direction. The rules are individual components inside groups. Each rule specifies match conditions such as IP addresses or ports and associated actions like allow, drop, or redirect. These are the building blocks of the policy enforcement in VFP. Next, coming to the key implementation features. Header transpositions or action primitives used to transform packet headers. For example, modifying IP addresses or ports. They allow VFP to rewrite packets on the fly, which is essential for NAT, tunneling, or redirection scenarios. VFP tracks the state of TCP connections such as SYN or FYN flags to better understand and manage flow life cycles. This enables stateful behavior where needed, improving control over long-lived sessions. The SSR allows the system to preserve connection and flow state during updates or migrations, avoiding disruptions. This is particularly useful in production environments where uptime and continuity are critical. The VFP leverages NIC offloading for actions like tunneling and flow enforcement. By pushing certain tasks to hardware, the system achieves high throughput while minimizing CPU usage. Coming to the next slide, API and update model. VFP API provides an interface that allows for fast and efficient updates to flow rules. This flexibility supports dynamic network configurations and ensures the system can adapt quickly to changes in traffic patterns or policy requirements, especially in large scale environments. One of the key features of VFP is State Save Restore (SSR), which enables system upgrades or maintenance to occur without requiring a reboot. This is a huge advantage in production environments where uptime is critical and minimizing disruption is key to maintaining service availability. VFP also allows for the non-disruptive deployment of network policies. This means that changes can be rolled out across production environments without causing service interruptions, improving network agility, and making the overall system more reliable. So, coming to the main results and evaluation, these charts shows the VFP performance gains across classification, throughput, and offload techniques. Coming to chart 1. This chart compares linear rule matching to VFP's classifier. As the number of rules increases from 1K to 20K, linear matching performance degrades significantly, while the classifier suits high SYN processing rates. This demonstrates the VFP classification engine scales far better with the rule count. Coming to the chart 2, here we can see the UFT dramatically improves packet processing per core. With or without layers, UFT nearly doubles the performance compared to no UFT, showcasing its value in optimizing the fast path. Next, coming to the chart 3, this graph highlights bandwidth improvements due to UFT and queue scaling. Using 8 queues versus 1 queue and enabling UFT increases throughput from a few hundred Mbps to over 10 Gbps, indicating that UFT and queue parallelism are key to bandwidth scalability. Next, coming to the chart 4, we can see that the comparison between NDIS to Packet Direct. Packet Direct significantly outperforms NDIS in packet processing per core. This validates the integration of Packet Direct with VFP, where RX throughput benefits from lower overhead and direct packet access. Next, coming to the performance metrics. The performance of VFP is drastically improved over a traditional linear rule matching, offering up to 100 times faster packet processing. This speed allows for real-time, high-volume decision making, ensuring low latency network operations and more efficient traffic management. By integrating with Packet Direct, VFP significantly enhances receive throughput up to 60%. This improves the overall network efficiency and ensures that more data can be processed in less time, especially in high traffic scenarios. UFT caching reduces the latency associated with flow lookups. Instead of recalculating flow information for every packet, the system catches flow data, which results in faster lookups and much lower network latency, even under heavy load. Coming to the evaluation summary. VFP operates globally within Microsoft Azure deployed on millions of hosts. This ensures that the same networking platform and performance are consistently available across all Azure regions. The platform is built for extreme scale, capable of processing petabytes per second and managing hexabytes of data. This makes it suitable for the largest cloud workloads and tenants. Altogether, these factors highlight how VFP meets the demands of hyperscale cloud environment while still delivering consistent reliability and high throughput. So we learned several key things from this paper. The first thing is stateful connection tracking is essential for enforcing real-world network policies at the cloud scale. The second thing is we saw how using independent logical layers per controller helps avoid policy conflicts. This is crucial for service coexisting in Azure. And the final thing is the paper demonstrates the importance of metadata um, based processing and fast path caching while enabling VFP to operate efficiently without heavy CPU load. Next, coming to the conclusion of this presentation, one major takeaway is that treating connection state as a core feature, not just an add-on, enables more intelligent flow control, policy enforcement, and seamless upgrades or migrations. VFP enforces strict layering, which allows multiple SDN controllers to manage different layers independently. This improves modularity, prevents misconfiguration, and ensures better reliability. Header transportations simply simplify policy implementation by offering a flexible general purpose way to modify packet headers useful for NAT, tunneling, and redirection scenarios. Features like state, save, restore, SSR enable upgrades and policy changes without interrupting traffic, which is critical for maintaining availability in cloud scale systems. The paper is very well organized. It starts with a clear explanation of the problem faced by the large scale public clouds, especially the need for host based programmable switching. Then it introduces the VFP architecture step by step, starting from layering, then stateful flow support, unified flow table, data transposition, and finally performance enhancements like fast path reconciliation and hardware offloading. Each technical feature is backed by a motivation, an implementation overview, and real world evidence from Azure. The flow from problem to design and design to evaluation is logical and it is easy to follow and shows thoughtful engineering. So that's all about this topic, and thank you.